Hey there! In this video, we're going to learn about eigenvalues and eigenvectors, and also learn how I can use those to diagonalize a matrix. So first up, we want to define what an eigenvalue and an eigenvector is. And we're looking at what happens when I take a square matrix, we'll call it A, and multiply it by some non-zero vector V. If I multiply these two matrices together, and the result is just a scalar multiple of the original vector V, then we say that V is an eigenvector of A. And that scalar multiple, we're going to call it lambda, is the eigenvalue, or n eigenvalue. Another way of looking at this, if you're thinking about vectors in terms of magnitude and direction, V is an eigenvector of A if when I multiply A times V, it only changes the length and not the direction of V. And the amount that it stretches or shrinks the vector is our eigenvalue lambda. And if V is an eigenvector of A, then any scalar multiple of V is going to have the same direction as V, and therefore it will also be an eigenvector of A associated with that same eigenvalue. And we'll look at that in an example. So that brings up the point that eigenvectors are not unique. If I can find one, any scalar multiple of it is going to be another eigenvector. So keep that in mind as we get examples and get answers, is that the answers that we come up with for those eigenvectors are not necessarily the only eigenvectors that would work. Okay, so for our first example, let's just try and wrap our heads around this idea of multiplying the matrix to get a scalar multiple. So let's say I have the matrix A, which is a 2 by 2 matrix with rows 2, 0, and 0, 3. And I have a vector V, which is just a column vector 2, 0. And I'm going to multiply these together and see if I can figure out what that scalar multiple ends up being so I can identify the eigenvalue. Okay, so I'm going to take A times V. Remember, we're multiplying matrices, so order matters here. And so I take those two and multiply. And remember, when we're multiplying, we take the first row of matrix A and multiply it by our column vector. And it's just the first term in each one multiplied plus the product of the next term in the row and the column. So 2 times 2 give me 2, plus 0 times 0 gives me a 4 for the first one. And then if I multiply the second row times our column, that's 0 times 2 plus 3 times 0, which gives me 0. So I end up with the matrix just 4, 0, which is really just the same thing as if I had taken the vector V and multiplied it by 2. And so I can demonstrate that 2 times the vector V is going to give me the same column matrix 4, 0. So 2 is an eigenvalue, and V is an eigenvector of the matrix A. Now, the second part to this question asks, well, what about 4V? So I'm taking my eigenvector V and I'm multiplying it by some scalar. And I want to see, well, is that also an eigenvector? And according to what we already said, it should be, and specifically for the eigenvalue 2 that we just found. Okay, so the eigenvalue there. And so if I'm going to do A times 4V now, well, I'll set that up. Let's take our same matrix A, and now 4V is just going to be 8, 0 is what we get from multiplying the vector V by 4. And if I multiply that, well, 2 times 8 is 16, plus 0 times 0 gives me a 16 in the top value. And then again, I get 0 for the bottom. 0 times 8 plus 3 times 0 gives me 0. Okay, so this time I ended up with just 16, 0, which is the same thing as if I had taken 2 times 4V. In that case, I'd do 2 times 8, and I get that 16. So 4V also worked out to be an eigenvector associated with the same eigenvalue of lambda equals 2. Okay, so now we want to figure out, well, how can I find eigenvalues when it's maybe not a more complicated problem than the one we just looked at? And how can I find eigenvectors as well? So this is going to involve the characteristic equation. Okay, so let's go back to our definition of an eigenvalue to develop this characteristic equation and a process for finding eigenvalues and eigenvectors. So our definition was that, well, a matrix A times V has to be equal to a scalar lambda times V. And so if I take this equation, I'm going to subtract the lambda V to the left side. So I get AV minus lambda V equals 0. And so I got a V in both terms. I want to be able to factor that V out, but lambda is a scalar. So if I pulled the V out of it, I can't take a matrix A minus a scalar. We don't have a definition for how to do that. But I can rewrite that lambda times, or I can turn that into a vector by multiplying lambda by the identity matrix. So I'm going to be able to factor out the V, and I now have A minus lambda I times V. Now remember, the identity matrix is a matrix with all 0 entries except for the main diagonal, which would be just ones. And we're always going to assume that this identity matrix is the same size as our square matrix A. Okay, now this actually represents a system of homogeneous equations. Might be hard to see, but I could take this matrix equation and turn it into a system of equations if I had all the entries in the vectors and the matrices. And so we want to come up with a non-trivial or non-zero solution to this system in order to find, lambda and V. So we got to go back to our linear algebra earlier units on these topics and pull out some facts. So we had a fact about inverses, and it was that a matrix A is non-singular, so it means it's invertible. If it is non-singular, then AX is equal to 0. That equation has only the trivial solution, x equals 0. So I don't want a non-singular matrix here. And the second thing is that about determinants. A matrix A is non-singular if and only if the determinant is not equal to 0. Okay, so we put these two things together. We want a determinant that is equal to 0 so that we get a non-trivial solution. And so this is our characteristic equation. We're going to take the determinant of A minus lambda I and set that equal to 0. And this will turn into an equation in terms of lambda that I can solve for lambda and find all of the eigenvalues for the matrix A. So this is what our process is going to look like. We're going to set up this characteristic equation. So the determinant of A minus lambda I equals 0. We're going to compute the determinant on that left side of the equation. And what we get from that is the characteristic polynomial. And we'll solve that polynomial for all values of lambda. And then once we have all of our eigenvalues, then we can plug them into the original equation we had there, that A minus lambda I times V equals 0. I can plug those in for lambda and solve for V in the equation. So let's look at an example where we can do this. Okay, so we want to find all the eigenvalues and eigenvectors of this matrix A, which is a 2 by 2 matrix with rows 4, 1, and 2, 3. So first thing I'm going to do is figure out what A minus lambda I is so that I can take the determinant of it. So I take my matrix A minus lambda times the 2 by 2 identity matrix. So that's 1, 0, 0, 1 is what that matrix looks like. And so really all that's happening is I'm going to change the numbers along the diagonal of my matrix A, and each one of them is going to get subtracted by lambda. So matrix ends up looking like this. So I have 4 minus lambda and 1 in the first row, and then 2 and 3 minus lambda in the second row. So only the diagonal changes when you do this. Okay, so that's my A minus lambda I. I need to take the determinant of that and set it equal to 0 to get the characteristic equation. So remember, to do the determinant, I'm going to multiply down the main diagonal going down to the right minus the diagonal going up to the right. So this is going to be 4 minus lambda times 3 minus lambda minus 2 equals 0. Okay, so there's a quadratic hidden in there. So I'm going to simplify this by distributing to get rid of all the parentheses. And so I get 12 minus 4 lambda minus 3 lambda plus lambda 12 minus 2 equals 0. And then I'll combine some like terms, clean this up. I end up with lambda squared minus 7 lambda minus 10 equals 0. At this point, you can use any method that you've learned in the past to solve this. If it's factorable, it's usually the first thing I try, and this one is factorable. It factors into lambda minus 2 times lambda minus 5, which means that my eigenvalues are 2 and 5. Okay, so I had a 2 by 2 matrix. I got 2 eigenvalues. That's going to be pretty typical, but not guaranteed. Okay, so we found the eigenvalues. Let's go on to finding those eigenvectors. So I'll start with the first one, lambda 1 equals 2. And I'm going to plug that into our equation, a minus lambda I times v equals 0. And I write these all in matrix forms, so we know what a minus lambda I is. We already found that matrix, so now I'm just plugging 2 in for lambda. So along the diagonal, I'm going to have 4 minus 2. It's going to give me a 2 in the first position, and 3 minus 2 gives me a 1 in the lower corner. And then the vector v, I'm just going to write that using some variables x and y, make it the right size to multiply by my 2 by 2 matrix. And the 0 vector is, I'm going to write that as a column vector as well. Okay, so cleaning that up a little bit, I get 2, 1, 2, 1 in the rows of my matrix. And so turning that into an equation, okay, it's the same thing twice, so I'm just going to multiply one row times our columns. So that's going to be 2 times x plus 1 times y, and that has to equal 0. Okay, so this I can then solve for one of my variables. I'm going to go ahead and subtract the 2x to get y equals negative 2x. So y is always going to be dependent on the x value. That means I can create an eigenvector from this relationship where x is 1, or 1 times some parameter t, we can say, and then that means that y would be negative 2 times that. So here it's written with a t. We pretty much, most of the time, are going to just let t equal 1 to get the eigenvector v1 equals 1, negative 2. Remember, eigenvectors are not unique, so I just need to get one that fits the pattern. And so this is a nice, simple one to use for that. Okay, so I got an eigenvector from lambda 1. Let's do the same thing with lambda 2 equals 5. Okay, so I end up with the same equation. I'm subtracting 5 from the main diagonal. So that gives me the matrix negative 1, 1, and 2, negative 2. And if I just grab one of those equations from multiplying the first row times xy, I get negative x plus y equals 0. Adding the x, that means x equals y. So they're always going to be equal to each other. I can write that as a matrix 1, 1 times some parameter t, or just let t equal 1 and say that v1 equals 1, 1. And I got a second eigenvector. Okay, so 2 eigenvalues and 2 eigenvectors to go with them. The next thing we want to look at is diagonalization of matrices. So a square matrix A is diagonalizable if we can write it as this product where A is equal to P times D times P inverse, where D is the diagonal matrix where the eigenvalues are along the diagonal, and so all other entries in that matrix are 0. And then P is the matrix we get from the columns, turning each column of the matrix into the eigenvectors. So if we took all the eigenvectors and eigenvalues we got from that last one and put them together, I can form D and P from that. And if it turns out that P times D times P inverse is A, we say that A is diagonalizable. And why do we care about this? Well, first of all, the A and D are similar matrices, and we can also say that D is equal to P inverse times A times P, assuming, of course, that P and P inverse exist. But one of the advantages of a diagonalizable matrix is it makes it very easy to do powers of matrices. We've talked about multiplication of matrices, but we never talked about raising to a power. And so diagonalization allows us to deal with these in a way that's a little less unwieldy. And particularly because d to the n is a diagonal matrix, which is much easier to take a power of than an is. Okay, so but today we're going to just focus on figuring out if a matrix is diagonalizable. So when is it diagonalizable? Well, again, we got to pull out some facts from a previous unit on matrices. First one, an n by n matrix is diagonalizable if and only if it has n linearly independent eigenvectors. Okay, so linear independence is the part that should be a little bit familiar. So if I get all the eigenvectors and it turns out they're linearly independent, then that means my matrix will be diagonalizable. Now, if an eigenvector of a matrix is associated with a distinct eigenvalue, then the eigenvalues are linearly independent. So for each eigenvector, it has a different eigenvalue. then I know they will be linearly independent. So this gives us a nice test that works in a lot of cases. I can say if we have an n by n matrix and there's n distinct, so different eigenvalues, then it's going to be diagonalizable because the eigenvectors associated with each one will be linearly independent. Now notice this doesn't say anything about a case where we have less than n distinct eigenvalues. It only tells me if there are that many that it is diagonalizable. If I have fewer, so maybe I get a repeated root from the characteristic equation, then it may or may not be a diagonalizable matrix, and I'd have to go back to proving that the eigenvectors I get are in fact linearly independent. And one way we can do that is by taking the determinant of P and making sure it's not equal to 0. Again, this is a fact coming back from matrices that we're kind of tying into this concept of eigenvectors. Okay, so there's two ways I can figure out whether a matrix is diagonalizable based on its eigenvalues and eigenvectors. So let's do an example after we go through the process. So how to diagonalize, diagonalize, not diagonalizable, a matrix. So first I'm going to find the eigenvalues, then I'll find the corresponding eigenvectors. And then I'm going to construct P and D, assuming that the matrix is diagonalizable. I'll construct P and D, and then just verify that P is invertible, that it has an inverse. And I can do that by just taking the determinant of P and making sure I don't get 0 for that. So let's look at an example. Okay, so we want to take the same matrix we've been working with, that 4, 1, 2, 3 matrix, and determine whether it's diagonalizable. So let's bring back the eigenvalues and eigenvectors that we found already for this. So I had eigenvalues 2 and 5, and then eigenvectors 1, -2, and 1, 1. Okay, so A is a 2 by 2 matrix, and we got 2 distinct eigenvalues. So we can use that fact that we just went over. If it's a 2 by 2 and there's 2 distinct eigenvalues, and I got an eigenvector for each one, then this is going to be diagonalizable. Okay, so it's just that easy when you get distinct roots. And so now to diagonalize it, I just need to identify what P and D are and make sure that P has an inverse. So D is going to be the diagonal matrix where the diagonal is the eigenvalues. So 2, 0, 0, 5 would be D. And notice, I mean, the order of the eigenvalues is arbitrary here, so you could flip-flop the 2 in the diagonal and get another matrix for D. To get P, I'm going to use my eigenvectors, use those as columns. Again, the order is arbitrary, so it's going to flip-flop depending on which one I call V1 and which one I call V2. So P is 1, 1 in the first row and -2, 1 in the second row. And now let's just make sure that P has an inverse. So I'll take its determinant. So the determinant of P, I'm going to do 1 times 1 down the diagonal going to the right, minus -2 times 1 for the diagonal going up to the right. And so that's going to give me 1 plus 2, so I get 3, which is not 0. So P is going to have an inverse. I don't need to find it. They didn't ask me to, but I know that it exists if I did want to go through the whole Gaussian elimination to find it. Okay, so the matrix is invertible, and I can say that A is equal to P times D times P inverse.